Hello, everyone. Welcome to another of SNEA's Networking Storage Forum talks. This time, it's on NVMe over Fabrics, focusing on discovery automation for NVMe IP-based storage area networks. A few things before we begin. In the top right corner of your screen, you'll see a little square sort of thing. If you click on that, you'll enter full screen, which blows up the text and makes it a whole lot more visible when you get to those slides later that have lots of very fine print on them. Also, we'd like to have your feedback, please. So before you leave, let us know what we did right and wrong about this so that we can continue to do better for you each time. If you can, go ahead and enter your questions as we go along. And occasionally I'll insert those questions for the speakers during the talk, but mostly we'll hold them for the Q&A at the very end of the talk. And any of those that we don't get to now will get answered as well in our blog that will appear in another week. So with that, this is me. I'm Tom. I'm your moderator today. Eric Smith comes to us from Dell, and Curtis comes to us from Hewlett-Packard, two companies who've been very deeply involved in NVMe since the very beginning. SNEA, the Storage Networking Industry Association, is 185 industry-leading companies and over 2,000 active contributing members, including the three of us on this talk today. And we do this for over 50,000 IT end users and storage professionals around the world. Technologies that are of interest to us, as you can see here, I don't have to read this for you. You get the basic idea. It's everything about storage. Technologies from securing to connecting to using to what happens when you sunset? How do you back up? Everything in between. I'm not a lawyer and I don't play one on TV, but I get to tell you the legal material here. The material contained in this presentation is copyrighted by SNEA, unless you see otherwise specifically noted on a slide. Member companies and individual members can use this material in presentations, but these slides have to be reproduced in their entirety without any modifications. And we do ask to be acknowledged for this. This presentation is a product of SNEA. Neither the author or the presenter is an attorney, like I warned you, and nothing in this presentation is intended to be or should be construed as legal advice or an opinion of counsel. If you need legal advice or information, please contact your attorney. The information presented herein contains the author's personal opinions and current understanding of the relevant issues involved. The authors, presenters, and SNEA do not assume any responsibility or liability for damages arising out of or any reliance on or use of this information. No warranties expressed or implied. Use at your own risk. So, to the real stuff now. Our agenda for today is an overview of NVMe over Fabrics and what is discovery and why is it needed. Then we go over several different methods of discovery, being direct and centralized discovery, and then we give you examples about this. So now we'll have our first, Eric Smith from Dell will begin with this.
Excellent. Thanks, Tom. So as Tom mentioned, we'll be going over providing you a quick NVMe over Fabrics overview and then get into the different types of discovery. Just to sort of level set about NVMe and NVMe over Fabrics, non-volatile memory devices like NVMe SSDs, flash drives can use a PCI interface rather than a serial I/O controller. And so when we talk about NVMe, we're talking about non-volatile memory express. It defines commands that allow interaction with an SSD or flash drive over PCIe. So many of you probably have heard 64,000 queues with up to 64K commands per queue. And That's where this comes from. This is NVMe. In reality, you know, many devices are not going to support anywhere near that, but that's where that comes from. And then NVMe over Fabrics describes how NVMe commands are transported over a network. And there are several different types of fabrics. You're probably heard about NVMe over Fibre Channel, NVMe TCP, NVMe RoCE, InfiniBand, and iWARP are also available for use. But what we're going to be talking about today is the new functionality described in Technical Proposal 8009 and 8010, which describe a standardized and scalable automated discovery process for IP networks. And so what TP 8009 and 10 are, we'll get into over the course of this presentation in quite a bit of detail. Before we get there, though, I mean, it's important to sort of acknowledge this evolving SAN space that we're all participating in. And when I say evolution, I'm talking about from SCSI to NVMe. And so when I think about how things have evolved, it starts with the application. So the application's running on a host that are accessing external array-based storage and block-based storage are typically either using Fibre Channel or iSCSI for that access today. So both Fibre Channel and IP networks are already supported. When NVMe drives were first introduced on the host and in 2015 time range, they were mainly used for caching and for boot drives. And once we saw the performance benefits that these applications were getting, and for these use cases, we started using them in the array, and the arrays also saw these tremendous performance improvements. It was like 30% was one early result just by using NVMe drives and the protocol in the back end of our storage products. And so it makes sense then that customers, as they're seeing the performance benefits of NVMe SSD, and they know we have NVMe SSDs in the array, that they'd want to use an NVMe protocol to access those drives. And so that's where NVMe over Fabrics starts to come into play. And so NVMe over Fabrics, again, it runs over Fibre Channel or Ethernet. We're going to be talking a little bit about both today, but primarily focusing on Ethernet and discovery. So when we talk about the different types of topologies that can be supported, or the different types of connectivity, layer one, I start with what we would typically consider a traditional enterprise type of deployment, a dedicated air-gapped dual SAN topology, so SAN A, SAN B, with the management interfaces obviously provided over IP. And that's very typical. The SAN A, SAN B here could be Fibre Channel or it could be IP-based. But we also support converged LAN and SAN sorts of deployments with, for the discovery protocol that we're going to be talking about here in a minute. This is where the IP, the LAN and the SAN are sort of converged onto the same set of switches, and you get to take advantage of all the great IP features like link aggregation and things like that. And so that's another topology we're interested in. Of course, people want to scale these environments up, and we believe that to do that, some customers would choose, again, a SAN A, SAN B fabric consisting of multiple switches. Again, this could be Fibre Channel or IP-based SANs, isolated from the IP LAN if it's IP-based. And then...
Eric?
Yeah.
Eric, excuse me, if I could interrupt for just a moment.
Sure.
We've had several questions from people about, I can't see the slides, the audio's breaking up. So I'm just making this announcement for everyone. We are not seeing any problems on any of our machines logged in either as presenters or as viewers. So we are suspecting that if you are having those problems, it is some sort of a network problem you are having with your connection to BrightTalk. So you may want to consider logging in again, see if that helps. Continue, go ahead.
All right, thanks, Tom. Sorry, everyone, if you're having troubles. Hopefully we get that resolved. And then the fourth type of deployment, I'd say, is where you're interested in using IP for your LAN and your SAN. You don't want to converge them, but you do want to use IP. So maybe you could have dedicated switches for LAN and for SAN. I mean, there's a bunch of different ways you can do this, and this is not an exhaustive list. I mean, there's many other ways you could do this. But we wanted to ensure that discovery would work on all of them. So what's the problem we're trying to solve? Well, NVMeoF's IP-based discovery problem is actually very well known and documented, and it's even acknowledged in the standard. So this text from NVMe over Fabrics 1.1 the method that a host uses to obtain the information necessary to connect to the initial discovery service, is implementation specific. This information may be determined using a host configuration file, a hypervisor, OS property, or some other mechanism. So, so what that means and why it's a problem, we'll get into in a second. But basically, it comes down to the methods described above all limit the scale and interop of any IP-based NVMe over Fabric solution. So to address this limitation, a group of companies in late 2019 got together and to see if we could agree on a standardized automated discovery process. And we ended up basing our approach based on Fibre channel Fabric services. And I get a lot of questions, well, why'd you do that? Well, the answer is that Fibre channel already provides a very robust automated discovery protocol. And almost everybody involved in the project had some amount of FC expertise. In fact, many of us were sitting on are participating in the NVMe standards body. So it made a lot of sense for us to go that way. It just sort of was natural for us to do. But it did turn out to be a bit more complicated than we had hoped and required two separate technical proposals to get it done. They are TP 8009, which handles the automatic discovery of NVMeoF discovery controllers, and the definition of a centralized discovery controller. And we'll talk about those in quite a bit of detail going on. But at the same time, I just wanted to point out that there were other bits of work going on with NVMe and NVMe over Fabric, specifically, security, so authentication and encryption, more specifically, secure channels, TP 8006 and TP 811 respectively, were being worked on and have now been ratified and are published. And we're also working on boot from SAN. We know that's important for a lot of customers, and there's quite a bit of work going on in that space as well. Interestingly enough, we just completed our 30-day member review of TP 8009 and TP 810, and so they're not quite ready for the public to view yet, but they'll be ready shortly. Okay, so when I think about discovery and I compare Fibre channel versus NVMe and IP-based SANs, I break the functionality required into two different buckets of functionality. The first is automated fabric formation, and this is basically describes the process that enables a group of switches to get to the point where they can pass traffic between endpoints. Each reachability is possible. The other bucket of functionality is automated end-to-end discovery. And this is what enables hosts basically to discover storage ports without you having to go to every host and configure them manually to point at a specific storage resource. And that's very typical with iSCSI. Now, Fibre channel provides the automated fabric formation piece, basically, through FCSW. There's a standard for this. Now, it is vendor specific. It doesn't interoperate between vendors, but it is rock solid and has been for a while. It's very, fabrics form very easily today without a lot of configuration, actually any configuration by default. The automated end-to-end discovery for Fibre channel, the discovery services themselves, such as the name server, sit on the switches, run on the switches. They're vendor specific, and the discovery clients are basically embedded in the HBAs, and so they're vendor specific as well. But the great thing is Fibre channel's been around for 20 years. And we've done a tremendous amount of interoperability work with it. So we don't really have interoperability problems, even though we've got vendor-specific solutions. They work together pretty much seamlessly today. On the NVMe TCP or NVMe IP side, rather, Ethernet IP fabric formation is vendor-specific. It's a little, I would say, it's a little bit less. It's a little bit less robust as Fibre channel is today, just because it hasn't been around for as long. It's one solution for that is Smart Fabric Services from Dell, which works perfectly fine, but it's for Dell switches. But there are many other solutions available today. And the discovery services themselves for NVMe IP SANs, we're going to talk about a centralized discovery service, or a CDC, that can run basically anywhere. It can run on a VM. It can run on the switches themselves, on a smart NIC, a lot of different places. But the idea is that it provides a service to the network that it's connected to. And the discovery clients are software-based. They sort of sit on the endpoints, and they handle the registration with the CDC, the discovery of each other, and all that. And we'll get into a little bit more detail later. So that's sort of how Fibre channel and NVMe IP or NVMe TCP sort of compare to one another and how the different services are provided. We're going to focus on the automated end of discovery piece throughout the rest of this presentation. So just a little bit about discovery with NVMe over Fabrics. It's just, you got to realize it's built around just these things called discovery controllers. And a discovery controller is a single location that reports all known NVM subsystem interfaces. So NVM subsystem is an array. Think of it, it's close. Think of it as an array, and you'll be right 99.9% of the time. The discovery controller simplifies administration because a single discovery controller IP can provide information about subsystem interfaces for multiple subsystems or arrays. So a single discovery controller can point you at multiple arrays. And in this context, the concept of a referral allows a discovery controller to point to another discovery controller. So you could get federations of discovery controllers all talking to each other and referring to one another. But a common implementation today is that every storage subsystem contains a discovery controller that only describes interfaces on that subsystem. So you'd connect to a port on the subsystem, you get back the interfaces that you can communicate with. Not completely unlike some of what happens with iSCSI. And then until recently, there was no standardized method for host, subsystem, or discovery controllers to register information with a single discovery controller, and the centralized discovery information that we're providing will cover this in a bit of detail. So some terminology, again, we mentioned centralized discovery controller, the CDC sort of sitting in the middle of the network. We also have endpoints. These are on host and storage subsystems, and they're identified by NVMe qualified names, or NQNs, and the IP addresses associated with them. Those are one way you can identify them. We also think of the IP network, or an IP SAN. And to create an IP SAN or an IP network, you can use most modern switches will work perfectly fine as long as they're 25 gigabit capable and above. That'll work fine. The subsystem itself, again, it's a storage array. It's sort of analogous to a SCSI target because everybody starts, as soon as you start talking storage, they say initiator and target. So if you're talking target, you're talking subsystem and NVMe terminology, although it's not really a target in that context. And again, they're identified by their NQN, and this should say WWPN in Fibre channel and IQN in iSCSI. The centralized discovery controller instances. Think of each CDC instance as providing discovery services for the endpoints that are taking part in a particular NVMe IP-based SAN instance. So an IP-based SAN is a collection, one or more networks that are allowed to communicate with one another. And for that collection of networks, there is a CDC instance that is providing the services that allow the endpoints in those networks to discover one another. We got an example coming in just a little bit to help make that a bit clearer. And then direct discovery controllers are the NVMe discovery controllers that reside on subsystems. And hosts could connect directly to storage via this direct discovery controller. So you can just point right at that DDC on the storage array and figure out what storage ports you can communicate with. But you'd lose the advantages of centralization that we'll go over here in just a minute. So when we first started down this path of working on discovery automation, we wanted to ensure that we supported three basic topologies. The first is physically connected, where you have a host physically connected to a subsystem or a DDC via a cable. And the reason that we wanted to support this, from my perspective anyways, was because we didn't support it with the first release of FCOE. And it turned out to be a really big limiting factor and hurt adoption. So we wanted to make sure we supported that physical connection, that physically connected topology. Direct discovery, that's multiple hosts and subsystems without a CDC in the network, was another important one. Not everybody's going to want to deploy a CDC. And as you'll see in a minute, CDCs really make sense at above a certain scale. So for smaller environments where they just wanted to put a bunch of hosts and subsystems onto a single broadcast domain or a small set of networks, direct discovery should work okay. And then centralized discovery, that's where multiple hosts and subsystems are working with a CDC in a network, and this allows large scale deployments. So we want to make sure we supported all three of those. Now, up until we started doing this work, direct discovery was how you did discovery with NVMe. And it basically worked by the administrator going to a host and having it connect, using the connect command to connect to a discovery controller at the IP address that's supplied by the admin. Now, this isn't really required by the protocol, but it does allow for the storage admin to get access, easy access to the NQN of the host. Otherwise, you'd have to figure out what the NQN of the host is and sort of sneaker nut it over to the UI and plug it in manually. Well, the Connect contains the NQN. So once the subsystem picks that up, you can go ahead and provision namespaces or storage volumes to the host NQN. Now, once that provisioning is done, you go head back over to the host and you go ahead and use like a command like along the lines of NVMe connect all to discover and connect to all IO controllers on that subsystem. Now, the downside of this is that now you get to repeat those steps 1 through 3 on all hosts, and you get to do it for every subsystem that you want to connect to. So that doesn't scale very well, and I'll show you why in a second here. Now, configuration steps with centralized discovery. This is the new thing that we're introducing. It's much more streamlined. It starts with the concept of registration and discovery with the centralized discovery controller. So the very first thing that happens, and this happens automatically, the host and the subsystems discover the CDC, connect to it, and register discovery information with it. Now, once that information's in the CDC, the SAN admin has the ability to go ahead and perform zoning just like you would with Fibre channel today. But it's optional. And the zoning is optional because each CDC is required to support something called subsystem-driven zoning. It's basically where the subsystem can send Fabric zoning commands to the CDC, and the CDC will enforce those zones automatically. And so how that would be used is basically once everything's registered and the subsystem admin is working with his UI, he can figure out what hosts are connected to the network, go ahead and provision namespaces to them. And then once those namespaces have been provisioned to the host NQN and IP address, again, that zoning information gets pushed out to the CDC. Then it gets enabled. And then once it's enabled, something called an asynchronous event notification is sent from the CDC to the host. The host comes to the CDC, says get log page, and figures out what IO ports they're allowed to communicate with, and then goes ahead and connects. Now, you would then repeat, worst case steps 1 and 2 for each host on each subsystem. But really, again, with subsystem driven zoning, you'd have one step here, step 2, which is to provision storage. Now, when we compare a direct versus centralized discovery at scale, what's really shown here on the right-hand side in this diagram, you have total configuration steps on the y-axis, number of hosts on the x-axis, and the orange line represents the number of configuration steps required for direct configuration, and centralized is the light gray. Now, what the chart really doesn't capture, it sort of points at 64, and what that line is, what that arrow at 64 is saying, that direct discovery becomes impractical around or above 64 hosts. And what it doesn't capture, the real reason for this is that direct discovery requires interaction with each host every time a storage subsystem is added or removed. So, not all configuration steps are created equal. So some of those orange configuration steps need to be done on different user interfaces or different panes of glass. So it gets cumbersome. Also, direct discovery may lead to extended discovery time if many subsystem interfaces are present. And think of a case where you've got 100 ports, 100 storage ports, and 100 host ports, all trying to, and all 100 host ports are connecting to all 100 storage ports, trying to figure out which of the ports provide storage for them. It gets really chatty and really inefficient. So, we think this, the sweet spot for the use of a CDC and centralized discovery is somewhere north of 32 and right around 64 ports is where it makes a ton of sense to use a CDC or a centralized discovery method. So just some additional points about discovery automation. Discovery automation does not depend entirely upon a centralized discovery controller. Again, you can use direct discovery and make use of MDNS as described in TP 8009, and I'll go into how that works here in a second. The approach does not allow for centralized control, and this means using MDNS does not allow for centralized control, and this means access control of the network is much more complicated and practical. So things like hard zoning would be very difficult to do, not using centralized control. Host will not be notified when a new storage subsystem is added to the environment is another reason why that direct discovery doesn't work that well. It's nice to get that asynchronous event notification and wake the hosts up to have them go out and automatically discover. And then the other thing is MDNS can become excessively chatty in larger configurations. We have some experience at Dell where anything over like 1,000 ports in a single broadcast domain was caused us issues in one situation. So just keep that in mind. Okay, so direct discovery, last couple of slides before I turn it over to Curtis for centralized discovery. So direct discovery, we're going to focus on the physically connected and the direct discovery use cases. And we're going to be talking about that because there's no centralized discovery controller in either one of these. But you can still, again, get automated discovery. And so when we think about discovery of subsystems, just to refresh your memory, the administrator, again, either provides an IP address for what we call a discovery controller, or they can discover this IP address via MDNS. And I'll show you how that works here in a second. But basically, you're providing the IP address of, you want to connect to these Ethernet ports on the storage array, and you want to connect to the discovery controller that we call basically in an entity called a discovery subsystem, which is shown under subsystems in the middle of the diagram. So the host would read a discovery log entry from that discovery subsystem, and that sort of the discovery log entries are shown over on the right-hand side of the diagram. And there's one entry for every subsystem that the host can connect to, and then they will go ahead and connect to those discovery entries. So that's basically how it works at a high level. Jumping down a level into how the actual automated discovery works, you have a new host coming online. Basically, the way that it would work is you connect that cable, the host would send out an MDNS query onto the network. And basically, it's looking for a discovery service called NVMe disk. And in response to getting that MDNS query looking for NVMe disk, the DDC would respond with some DNSSD records that include a TXT record containing the sub NQN or the subsystems NQN, as well as the protocols it supports, so TCP and RoCE in this case. And there would also be an A record that provides the IPv4 address of the discovery controller on storage S1. And in this case, it's 10.246.61.20. So once the host gets that, it can establish a transport connection between the host and the storage, and then send a connect to that discovery controller, initialize the discovery controller, perform get log page, and then go ahead and connect to any storage ports that it's allowed to. So that's how this physically connected cable works, and you automatically get access to the storage that's available at the other end of the cable. Now, occasionally you'll have a storage port come online after a host. And in that case, just wanted to show you that it works here as well. When the storage comes online, they'd send out a probe and an MDNS announce, and then the storage would pick up the fact that, hey, there's new storage that just came into the network. I will go ahead, establish a transport connection, and basically do the same steps I did in the previous example. And then a little bit more complicated is the multiple hosts and subsystems in a single broadcast domain. In this case, you've got host 1 connected with a dotted line and storage 1 is connected with a dotted line. Host 2 is a solid line, storage 2 is a solid line. And basically, you'll see that we send out MDNS queries from both hosts. It's both storage ports receive the MDNS queries. The storage ports, in this case, are sending a multicast response. They could also send unicast responses if they wanted to. Those responses would be received by the host. They get the IP addresses of the discovery controllers, establish their transport connections, and go ahead and connect. And then run that discovery, figure out where the storage ports that they can access are located, and continue on with down to the point where they'll be able to do I/O. So with that, I'm going to turn it over to Curtis for a discussion about centralized discovery, and then come back to you at the end with a discussion about with an example of how it all works together.
Okay, thank you, Eric. So Eric has given us a little bit of an introduction to the centralized discovery and explained some of why we went and did this work. I'd like to give you a little bit of a graphical view to help you visualize how we ended up where we ended up, and talk a little bit about where we are and what the model for centralized discovery looks like. So to start out, visually trying to take a look at the scaling problem. Each of the lines on this diagram represents a discovery connection to what's typical for today's storage systems. Each one of the storages around the outside is intended to represent a storage system, each with its own direct discovery controller using the model that Eric talked about a while ago as being the predominant model. Now in this picture, for most of us, these things are going to be a storage array. That's the SAN attached storage that we're all familiar with. But in the NVMe space, there are new forms of storage emerging that are going to be connected to this same type of fabric. For example, NVMe over Fabrics, JBODs or JBOFs, depending on what you want to call them, where you can have NVMe drives in an enclosure that can be direct attached storage replacement. And there are companies that are working on NVMe over Fabric attached drives that will attach directly to the fabric. So you can have a lot of different devices showing out here, and you can have a large number of connections trying to go to discovery controllers on each one of those storage systems. And as Eric mentioned, there is a model today called referrals that allows one direct discovery controller to refer to another direct discovery controller. And that does simplify some of the host manual configuration, as you only have to manually configure what you call your first discovery controller. But the referrals don't really scale well. You still require all of the host to discovery controller connections discussed in the last slide. In fact, we found they can actually increase the discovery time by reducing the parallelism for how the hosts go out and find systems, going out and finding one, getting the information back on where the next one is, and going down that chain adds to an already complex and slow boot process. And as we worked on implementation, we also found that there were some interesting, tricky things about referrals that made it more complicated than it at first appears. So what about cooperating storage systems? When the original NVMe over Fabrics discovery work was done, we wanted to define a complete enough model that people could start using this without spending forever doing a design. And we talked about that your storage systems can cooperate and share information with each other. And that is allowed, but through NVM Express 2.0, which released just this last summer, there's no method to enable that storage system cooperation. So that's kind of where we are today, that a capability that we talked about back in NVMe over Fabrics 1.0 that was too complex to justify defining at that time. Now we're to the point that people are deploying these systems and we need that model. In the cooperating storage system model, there's a little bit of a simplified picture. We can see that the direct discovery controller moved off of being one on every storage system to being some sort of a fabric entity where all those storage systems share their information with that direct discovery controller. In this case, every host just has one link over to that direct discovery controller and looks pretty good. But as we stated earlier, it does require some vendor-specific information exchange between the storage systems and that shared direct discovery controller. And there's limited, if any, deployment so far. And that only works to a certain extent. There's an interoperability problem with that. As much as we'd like our customers to only buy from our company, the truth of the matter is our customers want the flexibility to be able to buy whatever product best fits their needs from the companies that offer that. And as storage companies, we need to support the requirements of our customers. So when you get multiple companies' NVMe over Fabric storage systems into the same configuration, you start bringing in a mix of the individual discovery controller configurations and the shared discovery controller configurations. In this example here, we've got cat storage systems over on the left has their discovery controller, and mouse storage systems over on the right has their discovery controller. But as you all know, cats and mice trying to talk together does not always work perfectly well. So you can have every storage peer system can share a direct discovery controller, but as long as it's totally open to vendor implementations, it's going to be extremely difficult to get cross-industry cooperation. So that takes us to where we are today with the conclusion that we had to define centralized discovery controllers, and there's not much new on this slide. We've defined a standard model for cooperating discovery controllers with a single fabric entity that aggregates that NVMe subsystem information And one of the things that's new with these centralized discovery controllers, certainly new for NVMe over Fabrics, a little bit different than Fibre channel, is we've tried to architect so that Fabric entity for the discovery controller can be deployed in the model that best fits your storage architecture. It can go in a switch, it can go on a host, it can go on a storage system, it can be an independent floating object, and it's at the API level, at the NVMe Express command set management level. So there's flexibility in how best to deploy that. There is some additional new functionality for both the new centralized discovery controllers and the existing direct discovery controllers, which is the mechanism for host to register host information into the discovery controllers, and the mechanism for sharing those connectivity rules, the Fabric zoning information. And Eric talked about both of those a little bit as well. The registration information for the host, getting that information into the Fabric, we anticipate is going to really help with system management. So now where do we get to a world where things can play nicely together? In this diagram, we've got our cat storage systems over on the left that we had in our previous slide, our mouse storage systems over on the right, and we've introduced our dog storage systems in the middle there. This is kind of representative of my house, with the cats in the house, the dogs in the yard, and the mice hopefully out in the field. Sometimes the yard, occasionally the house. But if they all play together nicely and share their discovery information with a centralized discovery controller, then each of these hosts has one configuration to talk to the CDC with the automated discovery mechanism that Eric talked about earlier. That CDC information can be picked up automatically out of the Fabric, and your configuration time can be dramatically reduced, and your number of configuration steps is dramatically reduced, and all your storage can play nicely together. So what does the model look like for host discovering accessible subsystems? This is an important thing for making the centralized discovery controllers successful and easily deployed. What the group decided to do is that it was important that we make this be a clean evolution of the existing host discovery. In fact, we tried to make the centralized discovery controller look to a host almost exactly like the existing discovery controllers that hosts talk to today. So a host that connects to a discovery controller today is able to connect to a centralized discovery controller as well and get back the same format discovery log pages as it does today. And there's the same ability for filtering of which NVM subsystems that host is able to talk to as there is today. The only completely new functionality for the host is the registering with the storage Fabric. And that's an important functionality, but we've tried to design so that this method is backwards compatible as possible. The existing host can plug in easily, and then we work with the host vendors to get the registration functionality added in. How about the CDC discovery of the accessible subsystems? This one's kind of interesting, and I've received a number of questions on this. We ended up with two models defined. You probably all can understand, as technologists, we want to design the one perfect model that works for everybody and come to an agreement, but we couldn't get there for this case. So there's two models defined. One of them is called push registrations. And in that case, the storage system sends the registration information to the centralized discovery controller. There's another model for the CDC to pull registration information from the storage system. That one's called pull registrations. And so why did we end up with two models? Like I said, we really didn't want to have to do that. So the storage system registering with the centralized discovery controller and having that direct connection to that centralized discovery controller is the most direct configuration. It gives the storage system a connection straight into that centralized discovery controller, where it is able to immediately push information of interest. A new subsystem is exposed, it can immediately push that information into the system. And that's a model that a lot of us are familiar with, and there are some companies that really want to get to that sort of a model. That does add some complexity, though, and is a little bit architecturally different from how systems work today with NVMe over Fabrics, in that you now have your storage system that has to implement a little bit of host functionality and be able to make connections and send commands out to a centralized discovery controller. That is not a good architectural fit for some architectures. In some architectures, it's not a problem. Some architectures, it's not a real good fit, and it works best if the storage system information is pulled from the CDC to the storage system. So we've ended up with these two different models there. The goal is that today the functionality you can get with both of those is the same for the discovery in terms of the information that can be shared. There's a little bit of difference in the mechanism and the timing. There's some difference with some more advanced functions that for today are only defined for the push registration model. So for the registration model, the way push registrations work, those are proactive registrations from the host or storage system straight into the CDC. This is the only model that is defined for hosts. Hosts are required to push their registration information straight into the CDC. As I've said, for direct discovery controllers, that requires host functionality. And when you make the connection, then after the connection is made, NVMeoF admin commands are sent back and forth to perform the registrations. Poll registrations, those can only be used by direct discovery controllers. In that case, the storage systems discover the centralized discovery controller, and then they request poll registrations. And the CDC uses the existing get log page commands to read the existing discovery log pages. There's some additional functionality that the direct discovery controller has to implement if it supports CDC discovery, but it looks a lot like existing discovery models. So that's push registrations and poll registrations if you run into that. A quick example, this is a different view of the example that Eric showed earlier. And the host and the storage systems discover the centralized discovery controller up at step number 1. That uses the automatic discovery mechanisms defined in EP 8009. Once they've discovered each other, the host and storage systems register with the centralized discovery controller. The hosts read out discovery information from the CDC for what NVM subsystems are accessible. Then the hosts connect to those NVM subsystems. Here I show a couple of subsystems behind the direct discovery controller. The hosts discover the namespaces. I didn't draw arrows for that one. It's a pretty simple operation. And then go. This is a simplified model. There's some additional steps that could be done, but you wouldn't be able to see them. But what about, how does the centralized discovery controller filter the responses by host? In today's storage systems, they often, in fact, most of the time, implement some access management capability, some form of access controls that's often called mapping and masking. And that only reports information to hosts about NVM subsystems that are accessible to that host. The centralized discovery controller has to get the full list of all the NVM subsystems. So how does the CDC know which NVM subsystems are available to which hosts? And that is done by fabric zoning. We can't cover fabric zoning today. We're not going to have the time to go into it in any depth, so I've just given you one quick slide here to introduce you to the fabric zoning model. This is, as Eric mentioned earlier, in many ways very similar to fiber channel fabric zoning. We tried to take the capabilities of fiber channel fabric zoning that we know are used extensively and make them available. There's a couple of things that have been enabled that that you can't do in fiber channel fabric zoning, so it's not exactly the same, but there's some similarities. It's basically driven off of a zoning database. and that zoning database has two different objects inside of it. It's a list of configured zones and a list of active zones. And the configured zones is a list of all of the possible zones. Tried to create a blow up down here that shows a bunch of different zone groups that are in that configured zones list and a bunch of aliases for zones that are in that list. And then the active zones is the set of zone groups that are actively being enforced. Each of these zone groups contains zone members, which can be hosts, NVM subsystems, and zone aliases. And the way those members are identified can be off of your NVM NQN, NQN IP tuple, NQN port ID. There's several different ways of identifying the members with different levels of specificity to match the enforcement levels that we know that our customers require. And then there's admin commands defined for the centralized discovery controller and the NVM subsystem to share this fabric zone information. One thing that is a capability that we made sure we defined in here that some of our customers would like to have and some systems don't allow today is that you can have multiple active zone groups. So you can create different zone groups and have multiples active all at one time. So that's a quick introduction to direct discovery, centralized discovery, and a teaser on zoning. With that, I'll hand it back to Eric to walk you through a discovery example.
Thanks, Curtis. Yeah, we'll go through this really quick. I know we got a bunch of great questions queued up to go, so I just wanted to put all of this in context with a sort of an illustrated example. So, we've got an NVMe IP SAN fabric in the middle with host and storage connected to it. We've got a CDC, we've got some automated underlay config functionality. And when we start off the creation of an NVMe IP SAN, again, that automated underlay config will go ahead and make a fabric, enable that end-to-end IP reachability. Then we get into the server and storage subsystems, discover the CDC, again, using MDNS. They'll get the IP address of the CDC. Once they have that information, they can go ahead and register with that CDC. The CDC, once that information is in the CDC, an orchestrator or an operator can read that CDC name server database and set up the appropriate server and storage zones if they want to do that manually. They can also wait till the next step to go ahead and configure their volume, their namespace access on the storage and have the storage push that out automatically with SDZ, a subsystem-driven zoning. But in this case, we'll just say they set up the zones manually. The CDC then notifies the servers and storage systems, if applicable, that there was a zoning change. And in response to that, the servers will go ahead and do get log page to the CDC, pull down the IO subsystems that they're supposed to be connecting to, and then go ahead and connect and to automatically to the appropriate storage ports. And that, in a nutshell, is pretty much how it works, from end to end, top to bottom. Again, just some key takeaways really quickly here. Discovery automation does not depend entirely upon the presence of a centralized discovery controller. Smaller scale environments can make use of MDNS to automatically discover NVMe discovery controllers. The CDCs and subsystems that support interacting with them should use a feature that is called port local log pages. This is because it would provide a much better user experience overall and prevent leaking information between tenants. Maybe we do a future topic on that. I suggest make use of subsystem-driven zoning. Storage admins will then only need to interact with one UI for storage provisioning. Make use of extended attributes and register symbolic names that are meaningful to end users. NQNs are kind of a pain in the neck to work with if they're not formatted nicely. So, put additional information into those symbolic names and help users. And then finally contribute to the open source project called this NVMeoF discovery client that we're calling NVMe STAS. It's being led by Dell. It'll be available for public review after 8009 and 10 are ratified, and we're hoping that happens, before the end of the year. But it's the discovery client for Linux. And with that, I think we're at the end. And back to you, Tom, or we can take questions, however you want to do it.
Right. One comment first. anyone who wants to be involved in this open source project is welcome to do so. But unless they're a member of NVMe, they will not be able to have access to this until those TPs have been ratified, which is a good argument to be made for joining in the NVMe organization so that you can have access to those TPs before they're published. With that in mind, we'll start with some of the simple ones, like does this only work on IP4 or does IPv6 work as well?
It works with both IPv4 and v6.
Yeah, and since this uses NVM Express admin commands for the discovery information to go back and forth, you can actually implement the centralized discovery controllers even over a RoCE v2 configuration, though we do expect TCP/IP is going to be the predominant.
Okay. Now, with Fibre Channel, there's really only 2 HBA vendors and 2 switch vendors. So Interop works pretty well. For Ethernet, there are way many more NIC and switch vendors. How's Interop going to be assured in this more complex ecosystem?
Well, I mean, Fibre Channel has great interoperability because, 20 years worth of work. It wasn't always that way. And I remember back when we were working with JNI adapters and the nightmares that were involved with, some of the discovery issues that would come up. So, Fibre Channel's done a really good job in that space. With NVMe, again, this isn't a NIC thing. It isn't a switch thing. It's there's a CDC. The CDC is software. It will run basically anywhere. You'll be able to probably get one from multiple places. I know you'll definitely be able to get one from Dell. And there will be discovery clients that are standardized. So it's not on a per NIC thing. It's on a per OS thing. So VMware has a discovery client. Linux will have NVMe STAS, and there'll probably be other operating systems that will support it. I don't know, Curtis, what do you think?
Yeah, I think that's a lot of good points. And the number of the people working on this understood many of the pains we had with Fibre Channel back in the day as all this was being worked out. And so there's been a lot of work done to try and make sure that this is very carefully specified for exactly how all of this discovery should work together. And we're in a little bit of a different world today as well now. Dell's mentioned the NVMe STAS open source package that they're working on. And we've got some hopes that there will be a number of open source components that can be implemented and shared so that the industry doesn't have to waste time duplicating effort over and over again, and we can have good interoperability.
I agree.
Speaking of this NVMe STAS project, there are several comments about the CDC being used as a denial of service and not questioning how this works in comparison to NVMeoF, or not, excuse me, how this
Fibre
works
Channel,
compared to Fibre Channel, where we do have the ability to have multiple backup discovery controller systems.
Well, with Fibre Channel, you have a distributed name server. You have one per switch. You can certainly have a denial of service attack happen with Fibre Channel if you have a misbehaving HBA. Again, both vendors implement functionality now that prevents that from happening because it did. So I would expect a rate limiting function per request from a single host to be a feature that we would add over time. The other important thing is if you're going to create a SAN and you want SAN-like isolation and behavior, and you don't want to have to worry about denial of service attacks, deploy it as a dedicated SAN, an isolated SAN as an IP network, and that should help mitigate some of those concerns. Curtis, I don't know if you have anything you want to add.
Yes, I think that's a great question. I wish we'd said some things in here about that. We really didn't say much about it, but a core tenet early on in the work that we did was that the architecture had to allow for companies to innovate in the areas of resilience. And while the spec does not define how it's done, we carefully considered several times how we would allow companies to implement things like having multiple discovery controllers that were communicatively coupled and were able to share some redundancy with each other. We discussed how we would use some of the networking technologies that allow prevention of denial of service attacks and have load distribution over a large number of back-end servers serving a single front-end service. So this isn't intended in a enterprise class environment to simply be one little program sitting on a Raspberry Pi out there somewhere where somebody could unplug it.
Certainly. Okay. So will the discovery domains for this be limited to a single Ethernet broadcast domain, or are there mechanisms to scale out discovery for alternate subnets?
Curtis, do you want to take that one first?
Sure, I'll take that one. Yes, we discussed that this needed to be able to scale across multiple subnets. And the automated discovery piece is the trickiest one, where if you want to use the MDNS model, the spec talks about that you have to have some form of I call it a DNS responder that sits at your gateways between your different networks, so that when a device comes onto the system and broadcasts to find out if there's a centralized discovery controller out there, your DNS responder, sometimes called a proxy, sometimes called a forwarder, can announce that here's where your CDC is and give you the IP address for the CDC. You don't have to use MDNS, you can use standard DNS, and then DNS, of course, we all know works across multiple broadcast domains. And the actual communication between the hosts and the centralized discovery controller after the centralized discovery controller has been identified can run across multiple broadcast domains easily. It's just IP-based at that point in most implementations.
Yeah, I agree. That a lot of that. I agree with a lot of what you said, and you know, we not only is there a discovery with MDNS sort of consideration, but there's also when you think about you know, layer 3 IP fabrics in general, there are some routing challenges that you need to overcome if you're going to be crossing broadcast domains with storage traffic. And so we've done quite a bit of work in that space as well, making sure that we can support layer 3 configurations.
There's one very ambitious.
I love the question, the Flipkart question.
Yeah, yes.
Yeah, that's a great question. You know, one of the main contributors to NVMe-DEM reached out to me at SDC after SDC and having seen some of this content there. And we started talking about, you know, the differences between the two, Raj from Intel. And so it was a really interesting conversation. But as we started comparing notes, what became clear to me is that what we're proposing is a 100% in-band discovery protocol that's modeled after a storage networking, existing storage networking concepts. DEM uses some in-band, as I understand it, but also out-of-band. So it kind of has uses a different model than traditional storage networking does. I don't know. Customers are going to decide which one's better, which one works. I think they both work, and it's just really how do you want to handle it. I don't know, Curtis, if you have a different opinion.
Yeah, so I expect that NVMe-DEM will probably be able to be compatible with this model. Some of the core authors of NVMe-DEM were in the discussions while we worked on this model, and they're very aware of it. Yep. So while that model and that tool set was developed while there was the gap in the industry with no standardized way of addressing this functionality, we're all aware of each other, and I expect that we'll be able to to work cleanly together and make a robust ecosystem. And that's one of those tools that in the open source community that I think may end up being able to be built into other projects as we go forward.
Okay. Thank you all for coming today. Before you go, one additional thing to mention to you is that the slide deck is available now. If you go to the Attachments tab, you'll be able to download that immediately, and instead of having to wait to find it in our library at a later point. So please go ahead and give us your feedback. Rate this, and the slides will be available in our library as well. And as soon as we can, probably about a week, we will have all of these questions up on our blog for you to follow up with, and feel free to add additional ones to that. You can follow us on Twitter, and I believe that's pretty much it. Thank you so much for coming.
Thank you, everyone, for your time.
Thank you. Bye.